Good evening, everybody. Once again, Professor Ayorinde welcoming you to another session of organic chemistry. I hope you guys had a lively and enjoyable weekend. Karen, what are you saying?
Why does it say chapter 12 and 13, teaching two chapters at the same time?
Oh yes, we are going to cover both chapter 12 and 13 today. Chapter 12 and 13 today. Okay, anyway. Before we start the session today, I do have a few announcements to make. The first one is that the OWL assignment, we only have one more OWL assignment, which will be chapter 13. Chapter 13. That will be your OWL assignment, and that will be due on Tuesday, next Tuesday at 11 p.m. So you don't have to worry about doing any homework assignment during your Thanksgiving period.
Bless your heart, you are a very nice teacher.
Yeah, that's very nice of me, I know that. We have class next Wednesday.
What? Excuse me?
Yes.
Excuse me.
No, I mean, she's asking, Sinead is asking, do we have class next Tuesday?
Why did you say Wednesday now?
You know, I'm saying that is Wednesday. Yeah. There's class till next Wednesday. So anyway, so the OWL assignment, the homework assignment will be on chapter 13, and that will be due 11 p.m. next Tuesday. The other announcement is that we are going to do the online review session next Monday, not this Wednesday. So this Wednesday there will be no OWL online assignment review, but next Monday at 8 p.m. there will be an online review for OWL. I will send you a reminder for that. Also for the OWL assignment, there are some problems you don't have to do. I will email you to let you know what problems to omit. Also have your last exam out there, so I'll make sure you stop me 5 minutes before the end of class today so I can give this back to you. By the way, how many of you got a chance to see the webcast? The first one? Sort of.
It didn't work.
It did not work?
Yeah.
What happened?
It was completely hard to understand.
Slow when it doesn't slow.
Was slow? About the second one?
They were both like, it wouldn't load, and when it did load, if you tried to like move the bar, it would go, it wouldn't work.
Oh, is that right? I didn't have that experience. Anyway, okay, so we are going to... so what we're going to do now, we are going to start chapter 12, so 13. These two chapters will be covered in about 3 different lectures. Hopefully we'll finish all of the lectures before you go on Thanksgiving. So when you come back from Thanksgiving, all we are going to be doing will be just review sessions. Okay. Chapter 12 and 13. This chapter, of course, is concerned with the structure determination. We are going to be dealing with instrumental analysis, so to say. And particularly, we are going to focus on mass spectrometry, infrared spectroscopy, abbreviated as IR. And finally, we shall discuss nuclear magnetic resonance spectroscopy. And under nuclear magnetic resonance spectroscopy, we are going to discuss two topics, which will be proton NMR and carbon-13 nuclear magnetic resonance spectroscopy. Okay, just as usual, we normally do, for this chapter, this slide here gives you a list of items that should guide your study of the content of this chapter. For example, if you take a look at this, you see the first one here says, at the end of this chapter, you should be able to write the structure of an organic molecule based on its mass spec data. In other words, if we give you the mass spec data of a molecule, you should be able to give us the structure. Similarly, if we give you if you identify you should be able to identify the major mass spectrometric fragment ions of an organic molecule. And if you go to items 11 and 12, this said use MS or IR and NMR data to determine the structure of an unknown molecule. In other words, if we give you the data from each one of those instrumentation, which would be mass spec, infrared, and nuclear magnetic resonance spectroscopy, you should be able to construct the structure of an unknown compound. So these are the kind of things we are going to be doing during the course of these two chapters. Okay, at this point, I'm sure most of you want to know what kind of information do you get from each one of these instrumental analysis data. If, for example, let us take a look at the mass spectrometric data. If, for example, we have this molecule here, with the mass spectrometric data, you will be able to tell the molecular weight of this molecule. The mass spec data will give you the molecular weight of an unknown molecule. So therefore, we should be able to determine the molecular weight of this. It might also tell you, give you some information about structural information about the molecule. It might tell you that you have this group in the molecule. It will also tell you that you have a methyl group in the molecule. So by putting all of those pieces together, you should be able to construct the unknown molecule based on the mass spectrometric data. Now, when you get to the infrared data, what kind of information does infrared spectroscopy give you? The infrared spectroscopy, for instance, will tell you that this molecule contains a carbonyl group. Okay? So it will tell you this molecule contains a carbon-oxygen double bond, which is a carbonyl group. And so therefore, a combination of the infrared spectroscopic data and the mass spectrometric data, you should be able to construct the structure of the unknown molecule. And when it comes to the nuclear magnetic resonance spectroscopy, here, now this will tell you a lot more about the molecule. It will tell you about the electronic environment of this molecule. It will tell you that in this molecule, the methyl group is next to the methylene group. it might tell you that the methyl group is attached to the carbonyl group. So now you put all of those pieces of information together, you should be able to construct the structure of an unknown molecule. So whenever you use any one of those instrumentation, therefore you will be acting as a detective. We're giving you a set of data, and then you are supposed to construct the structure of that unknown material. So this is a very interesting set of chapters. These chapters 12 and 13, even though we do not have chemical reactions there, but they do actually force you to do some thinking. I know you guys like to think. So this is a chance for you to do that. Now let us now begin to take a look at mass spectrometry. What is mass spectrometry? Can anybody tell me what mass spectrometry is? Yeah, Tony.
Is it the generation of charged species and detection of their gases?
How did you know that?
I'm so smart.
Okay, very good. That's excellent. That is correct. Mass spectrometry. Mass spectrometry is the generation of charged species and detection of the species once you generate these species. In other words, we could place in mass spectrometry, we could, for example, let us say, for example, we have a molecule of carbon dioxide. Let's say we have a molecule of carbon dioxide. In mass spectrometry, if we place this sample of carbon dioxide inside the mass spectrometer, what we will get we will convert this neutral carbon dioxide molecule into what we call a charged species. And what do we mean by that? If you look at this, what the mass spectrometer does is to remove one electron from your neutral molecule, and upon removing one electron from your neutral molecule, it could form what we call a charged species. In this case, the species is positively charged. It could also add electron to the neutral molecule. In that case, it forms a negatively charged species. So therefore, what the mass spectrometer does is to form or to generate charged species, either positively charged or negatively charged. And once we do that, then it determines the mass. Then it determines the mass of this molecule. In this case, we say this molecule contains a mass of 44. But how does it do that? It does that by measuring the mass to charge ratio measures the mass to charge ratio of the ions that are being generated. In this particular instance here, in the case of this molecule here, carbon dioxide, of course we know the mass of carbon dioxide is 44. The mass of carbon dioxide is 44, and then it will divide that by the charge. The charge in this case is only 1. Okay, so therefore you get what we call mass to charge ratio, which is m over z. By the way, this is abbreviated as m over z. M over z, mass to charge ratio. The z stands for the charge. Of course, the m is for the mass. So now you have what we call what we have a mass to charge ratio for this molecule of 44, and therefore you know that the mass to charge ratio essentially does represent the molecular weight of carbon dioxide. So that is how the mass spectrometry works. In other words, it takes a neutral molecule forms a charged species from it, either the positively charged species or negatively charged species, and then determines the mass of the charged species. And by determining the mass of the charged species, we get the molecular weight of that particular molecule. But let us give you a little bit more detail about this. Okay, so what we have here, we have our neutral molecules. So we have a neutral molecule. In the mass spectrometer, we direct a beam of light or a beam of electrons, into the sample, and that beam of electron is very high voltage electron. Of course, that will knock out one electron from your neutral molecule, and then you form your charged species. Okay, then you form your charged species, which is right here. And this, the first charged species that you form is what we refer to as a molecular ion. We call this a molecular ion. And of course, the molecular ion we represent by M plus is a radical. It's a radical charged species. In other words, since we remove one electron from here, we have a free radical here. So now you have your charged species, and that is what we are going to measure to determine the molecular ion for that particular molecule. Now that is not the end of the story. Now what then happens? The molecular ion that is formed, which is right here, let us imagine that we start with this molecule here. It is 2-methyl, 2-hydroxybutane. Let us say we start with that molecule. And of course, this molecule is now charged. We form a positively charged species. At this point, notice we do not know exactly where that charge is. The charge could be anywhere within the molecule. And the molecular ion that is formed, which is this here, is so energetic that it begins to break into pieces. It begins to fragment. And the first set of fragmentation that you're going to get, of course, some of the easiest fragmentation will be to cleave this molecule here. Begin to get some kind of cleavage. If this is cleaved here, then you get this fragment ion. Now if it cleaves right here, you get this fragment ion. Now in this particular case, since we also have an hydroxy group in this molecule could also lose water, or the molecular ion could also lose water, okay, through dehydration, and then you form another ion here. And then what happens? So the instrument simply now collects all of these ions, both the molecular ion in this case, and what we call the fragment ions, which are all of these here. Now make a plot of all of this. So you may get something that looks like this. In this particular instance, so we have an ion, we have the charge M/Z, and then we have an ion, the molecular ion at 88. You will see a peak at 88. You will then see another peak at 73. You see another peak at 59. Of course, another peak at 70. In other words, a graphical representation of all of the ions, both the molecular ion and the fragment ion, is what we refer to as the mass spectrum. So the graphical representation of all of the ions that are formed, including the molecular ion and all of the fragment ions, the graphical representation of all of these ions is what we refer to as the mass spectrum. And based on the mass spectrum, we could therefore now begin to construct the structure of the original molecule. Now, if you take a look at this here, you see what happens here. We have a molecular ion at 88, and then we have an ion at 73. So what we normally do once you get that, you have 88 minus 73. That is 15. What does that suggest the molecule contains? If the molecular ion is losing 15 mass units, what does that suggest to you? What would that suggest to you? It has a methyl group. In other words, that tells you the molecule has a methyl group. Okay? Now, in this case, we also have a molecular ion at 88, and then you have a fragment ion, in this case what we call a rearrangement ion, at 70, and so this 88 minus 70 gives you 28. I'm sorry, 18. Sorry about that. Gives you 18. What would that suggest to you? That suggests to you that the molecule has lost water. For the molecule to lose water, that means the molecule contains oxygen somewhere. It could very well be an hydroxyl group. So these are the kind of things that we do with mass spectrometry. It's almost like a jigsaw puzzle. Indeed, for all of the instrumental analysis, including the IR and the NMR, it's almost like a jigsaw puzzle. You have a set of data, and you begin to put together the structure of your compound based on the data you are given. Okay. Now, there are some very common fragmentation that we find in the mass spectrometer when the molecular ion is generated. This is what we refer to as the alpha cleavage, and that is essentially what you find in this fragmentation here. This here some of the common cleavages that you find in mass spectrometry is what we refer to as alpha cleavage. And alpha cleavage simply means a cleavage that is next to the functional group of interest. In this case, you have an hydroxyl group attached to this carbon. So this carbon bond, this is your alpha cleavage right here. So that is very easily cleaved. You get a cleavage here, and that is how you get this particular fragment. You also get another alpha cleavage on this side, and that is why you get this fragment. So alpha cleavage is very, very common in mass spectrometry, and it does allow us to determine the structure of the original molecule. And of course, you also have what we call a rearrangement ion. In this case, you get this type of ion here as a result of the loss of water. Anytime you have an even number ion, in this case you have 70, anytime you have an even number ion, the chances are that is due to some kind of rearrangement, in which case you are losing molecules like water, ammonia, or neutral species. Okay, so we have two major types of fragmentation. which is alpha cleavages, and then rearrangement ions. There's another type of fragmentation that is also very useful in mass spectrometry, and that is what we refer to as McLafferty rearrangement. McLafferty rearrangement. Okay, let me go to a blank page to illustrate that for you. For the McLafferty rearrangement, if I have a carbonyl group, let us imagine that I have some kind of group attached to this carbonyl group. That group could be anything. I will tell you more about that later. Let's say this is just an R. And then we have here let's say another R here. This R here, of course, could be different from this R right here. Now, this carbon attached to the carbonyl, we refer to this as the alpha carbon. And of course, the hydrogen attached to that carbon is also referred to what? As what? Alpha hydrogen. And this here, the next carbon to that is called the beta carbon, and the next one to that is called the gamma carbon, which also means that the gamma carbon is also, whatever hydrogen is attached to it is called the gamma hydrogen. So anytime you have a carbonyl group, and that molecule also contains a gamma hydrogen, that's what we call a McLafferty rearrangement. And how does that happen? Now note that in this molecule here, let us say that the molecule is already been turned into ion, a positively charged ion. In this case, we have removed one electron from this oxygen here, so you only have this here. Okay, so this is your molecular ion, M plus, that is your molecular ion. So the molecular ion, anytime you have an alpha hydrogen, what happens? There will be homolytic cleavage in which the alpha hydrogen will transfer itself to the oxygen. In other words, we will be breaking the carbon hydrogen bond to the gamma hydrogen, and in so doing, the electron that is left here, notice this is a fish hook arrow. Only one of these electrons is breaking away, and this other electron will come here. And then, to complete the breakage, this electron will come here. And of course, this will simply stay right here. And then what do you get? The oxygen is still here. Now the hydrogen is attached to the oxygen. And of course the positive charge is still here. Notice that this electron here is used to bond to this hydrogen because the hydrogen is coming with only one electron. And now here, the CH2 is still here. Now notice also that this carbon-carbon bond is also broken homolytically, and that electron is here. And now you then also form, you lose this part of the molecule, as a neutral species. This part of the molecule is lost as a neutral species. And now you have this ion here. Now this ion, of course, could be stabilized by resonance, and that is why McLafferty rearrangement works. Could be stabilized by resonance. You could draw another resonance contribution for this, in which you simply move this electron to here, and one electron goes here. And now this is still here, and of course now this is still positively charged with one electron. So this is what we call the McLafferty rearrangement, in which case you have transferred a gamma hydrogen. What have we done here? We transfer a gamma hydrogen to the oxygen of the carbonyl, and in so doing, we are going to break the what we call the beta bond, so that you lose this nuclear species. Now, why is this important? Take a look at this R here. If that R, if the R is a metric group, that ion, M over Z, will be 58. What would it be? That would be 58. Supposing it is an ethyl group, this is this here, this R here. Okay? Supposing it is an ethyl group. Okay, let's do the math. Okay, you have ethyl. If this R was an ethyl group, that's CH2 plus CH3. That is 29, right?
Hold on.
Okay. Which one?
What figure are you referring to?
This R, this here. Okay.
That one.
This R, this here. Okay. Now, if that R, let us imagine that R was an ethyl group. Okay, that is 29 plus what we have here, oxygen and hydrogen. That's 17. This is the kind of thing that you have to do when you're dealing with mass spectrometry. You must have your calculator ready so that you will be doing some adding and subtracting. Okay, so you have oxygen and hydrogen, that is 17, the carbon is 12, right? And then this CH2 here, that is 14. And what does that give us? What does it give us? 70. That's 72? That should be 72. Okay. So if that R was an ethyl group, then you get an ion at 72, M over Z 72. Now supposing the R is an OH group. Supposing the R is OH group. Supposing the R is OH group. What does that mean? That would mean 17 again, 17. OH is 17. Plus another 17 here, plus the 12 here, plus the CH2, which is 14. And what would that give you? What would that give you? That should be 60, right? Okay, so that should be 60. In other words, the McLafferty rearrangement gives us some information. Now, if we say we have a methyl group, so what that is telling us is that we have a methyl group attached to carbonyl. If we say we have, if you see an ion at 72, what that tells you is that you have an ethyl group attached to a carbonyl. Plus also, it is also telling you that you have a gamma hydrogen. Okay? So, based on the information that the data gives you, you should be able to construct the original molecule. Okay, let us go back to the lecture material. Now, let us start beginning to work on problems. What we have here, we have the mass spectrum of, what is the mass spectrum of that compound? What is the name of the compound in that mass spectrum? What is it? What is it? What is the name again? Acetic acid. This is the mass spectrum of acetic acid. What do we see here? We see a molecular ion at M/Z60. We see an ion at M/Z45. Then we see an ion at M/C43. Okay? So if I ask you, what is the fragment at M/Z43? What does that represent? M/Z43, what does that represent? What does it represent? What is it? Okay. That would be this right here, right? That's M/Z43. Okay. Now, what about M/Z45? What would that tell you? M/Z45. M/Z45 will be this part of the molecule. Okay? So if I did not tell you this is the mass spectrum of acetic acid, and all I give you is this mass spectrum here, and I say, okay, of course the molecular ion is 60, it tells you that is the molecular weight, and say, give me the structure of that compound. You should be able to do that. In other words, you say, okay, 45 is this. If 45 is this, which is the carboxyl group, and you know that 43 is this, okay? It's just a question of not putting the pieces together, okay? Because this carbonyl is this carbonyl here, okay? And you know that the molecular weight is 60, okay? By putting together all of those information, the molecular weight and all of the fragment ions, you should then be able to construct the structure of that molecule. Is that clear? Yes.
So 43, it will always be a carbonyl attached to CH3, always.
Okay, yeah, that's a good question. The question Sinead is asking, will 43 always be, M/Z43 will always be the carbon the methyl attached to carbonyl? Not always, but very often it will be. But I will tell you some other possibilities. Okay. Now let us take a look at the mass spectrum of this other compound here. Of this compound here. This is compound we call acetophenone. Look at what we have here. The molecular weight of this compound is 120. You see a molecular ion at 120. So, if we did not give you the structure of this compound, we simply give you this data here. For example, this data also could be given to you in a tabular form. We could give you the data in this form. We say MS data M/Z 120. We say that is the molecular ion. Instead of giving it to you in a tabular form, in a graphical form as you see here, it will give it to you in a tabular form. Say that's 120. Then you have 105. Then you have 77. Okay, then you have 43. Okay? Now, in this particular instance, of course, we know that the the molecular ion is this molecule here. What is the ion at M over Z 105? What do you think that will be? Exactly. Minus the metal. In other words, that would be this here. So the M over Z 105 will be the loss of metal from the molecular ion. And that will be this ion here. Very often, since we do not know where the charge is, we could simply have a bracket around the ion and then have a charge with the electron next to it. Okay? So this would be your M over Z. This would be your ion at M over Z 105. Now what would be the ion at 77? M over Z 77. Anybody has an idea what that would be? M over Z 77. What will it be? Minus 43, exactly. If you take 120 minus 43, and that is 77. And what is 43? 43 is this here. Right? So what is 77? Benzene. So anytime you see 77 in the mass spectrum of any compound, you know you have benzene in there. Anytime you see an ion at M over Z 77, what that tells you is that that molecule must contain a benzene fragment. Okay? So these are the kind of things that you do with mass spectrometry.
I have another question.
Yes.
There's other lines there. So how do you know what line is?
Yes. That's a very good question. Now, what is going to happen is, when we give you the data, you simply take some of the more obvious data. This 51 here is actually coming from the, I'm sure this is the one you are talking about, right? That is actually coming from the benzene. Anytime you have benzene, that also gives you 51. But that's a lot more complex to explain. That is why I did not even want to touch on that. But generally, you will be given ions that are much more obvious that you could deal with. Okay. Okay. Now let us take a look at this molecule. Yeah, there's another aspect of mass spectrometry that I have not told you before. The most abundant ion in the mass spectrum is referred to as the base peak. In other words, the most abundant ion, the most intense ion in the mass spectrum of any given compound is referred to as the base peak. And all the other ions are plotted in reference to the base peak. Okay, now you take a look at this molecule here. Okay? The alpha cleavage here gives you M over Z 43. That's methyl attached to carbonyl. And then the McLafferty rearrangement here gives you M over Z 58. What that simply tells us is that you have a methyl ketone. That tells you have a methyl ketone because of the McLafferty rearrangement at 58. So this here, because of this methyl here, that McLafferty ion now becomes 58. So just taking a look at this here, without knowing knowing that this molecule is this, you should be able to construct this molecule here, given the fact that the molecular ion is at m/v 114. Okay, before we leave mass spectrometry alone, let us do a couple of problems. Okay, let's do this problem here. Let us try this problem. We have a ketone. Sinead, will you go ahead and read that question for us? See the kind of shape. Can you see? Okay, Cinda, go ahead.
I can't read because I'm reading.
This one here. Oh, you don't have your glasses too? Okay, Jessica, go ahead.
The ketone was M plus equals 86 and fragments at MZ equals 71, MZ equals 58, MZ equals 43.
Okay, very good. It says we have the ketone, molecular ion is 86. What does that tell you? What does the molecular ion tell you? This is the molecular weight, right? Okay. So you have a ketone at m/v 86 as the molecular ion, and then you have fragments at 71 and 58 and 43. Okay? Can you construct the structure of this unknown?
Yeah.
What is it? When you do this, start with the most obvious information. What is the most obvious information here?
43.
43? Okay, very good. So you have an ion at 43, so everybody knows 43 now. Okay, so you know you have in that molecule, that fragment. And then also notice here, we have an ion at 58. It says a ketone. What that tells me, and it is even number ion, what that tells me, that is a McLafferty rearrangement ion. And what does that mean? You already have the ketone here, so then you must have a gamma hydrogen. So that means I have to draw this to give a gamma hydrogen. Okay, that is alpha, that is beta, and you have gamma hydrogen right here. Okay?
So every time it's an even, it must be here.
Yeah, if it is a ketone, yeah, I mean, see what you do, it's almost like you say, okay, I think this is what it is. If it isn't that, then you can go back to something else. But you start with something that is obvious. You see an even numbered ion, okay, in this case 58, we know it is a ketone. The chances are you could be dealing with a McLafferty rearrangement. And for you to have a McLafferty rearrangement, you must have a gamma hydrogen. Okay? So in this case, this is alpha, beta, gamma. Okay, if that is the case, okay, let us explain the ions here. Based on what I've written here, let us explain the ions. This is the m/v 43, right? Then we have m/v 71. What would that be? That's m/v 71. So that explains that.
Wait, 71 is with the ketone?
Yeah. Okay, lots of methyl, and because of the McLafferty rearrangement, we simply have a transfer of hydrogen 2 here. Okay, we have a transfer of hydrogen 2 here, and this one is clipped, so we have an ion here. And that would be your McLafferty ion right there. Okay, which is your m/v 58. So, in essence, this is this molecule here, because this molecule here gives us a molecular weight of 86. That would be that molecule right there. If you add all of these pieces together, If you add all of this together, you get a molecular weight of 86. Huh?
Wait, so why do you draw the...
Which one?
Why do you draw the MZ58 on there? Is that even the answer?
No, what we want to do is to explain each one of those ions.
Oh, we have to explain them.
You see, we are simply saying that is how you got the 58. That is the justification for how you got 58. The 58 is a result of the McLafferty rearrangement. Okay?
If you take a table with all these,
Huh?
well, it's like, if you took a specifically, like, can't you just, like, make a table of, like, all your numbers?
To do what? Say that again.
Yeah, like, you know how we made a reagent table?
Mm-hmm.
You make a table with, like, the
Yes, okay, that's the next thing I want to do now. Okay, but let's do this one, then I will give you a list of possible fragment ions in mass spectrometry. Okay, now, in this one here, in this particular case, I will tell you the ion at M/Z72, what they've done here is to give you, of course, the mass spec data. They've also given you the percentages of all of the fragments. For the most part, that is not really that important to you. Okay? So I wouldn't worry too much about percentages at this point. But what is important here is that you have an ion at M/Z72, that is your molecular ion. The ion at 73, do not ignore that. That is due to isotope. Yes. Listen. We will tell you. Okay? We will tell you this is the molecular ion. Okay. Okay, so you have a molecular ion at M/Z72, then you have fragment ion as 57, 43, 29. Okay, let us put that that molecule together. What do you think that molecule will be? Anybody want to try that? What will be the structure of that molecule? Molecular ion is at M/Z72. We have an ion at 43. Start with the most obvious information. Okay, CH, okay, good. So we say we probably have this. Okay. And then, what is 57? Oh, well, yeah, what is 57? (43 plus 14, right? That is 57. In mass spectrometry, you learn to add masses together. Okay, so 43 plus 14, that is CA2. That is 57. That is that is CA2 here. Okay. And then, what is 29? What is 29? 14 plus 15, that's 29, right? 15 is methyl, 14 is methylene, okay, right? So that would be this. Okay, do we have all the physics in place? If you add this together, the molecular weight of this is 72. Okay, and where is the 29 coming from? Okay, the 29, when if you fragment from this side, that is 29, right? You see that?
Yes.
Okay, and if you fragment from this side, that is 57, and of course this whole molecule here is the molecular ion is 72. So you see how easy this is, right? It's really easy to put this together once you know the basic information. Now, before we leave mass spectrometry, I want to give you a list of common fragment ions. List of common fragment ions. start with M over Z. 77, that simply tells you you have benzene. Something attached to benzene. You have 91, that tells you you have benzene attached to either a CH2 or in which the attachment is here, or you have benzene attached to a CH3 in which the attachment could be anywhere on the benzene ring. So that would be M over Z 91. If you have 105, the chances are you have benzene attached to carbonyl, or benzene attached to methylene group. Of course, you all know about 43. 43 will mean a metal attached to a carbonyl. It could also mean isopropyl group. In case this hydrogen has. It could also mean an isopropyl group in which the attachment is to this carbon here. That is also 43. It could also mean a propyl group in which the attachment is on this carbon right here. So these are the three possibilities for M over Z 43.
Most of the time it's going to be the CH3.
Yeah, most of the time. Say that again.
Most of the time it's going to be a CH2.
Most of the time the metal attached to carbonyl is a lot more pronounced because of possibility of resonance. So that is generally what we find in most cases. But each one of these other fragments are also possible. Okay, so M over Z 45. It could be this carboxyl group in which the attachment is to this carbon here. Yeah, these are the more common fragment ions. Okay, so when you see this, of course, the first thing that comes to your mind is any one of these species. Now, this does not mean that this will always be the case. That is why you almost have to play detective, because there might be some other information given to you that might lead to something else. Okay. Okay, so now at this point we have come to the end of mass spectrometry. So what we are going to be doing once we finish the rest of the instrumentation is to begin to do a lot of programs. So once we finish all the basic information gathering, we are going to simply do a lot of programs. Now, believe me, I promise you we are going to be doing a lot more programs. Because the best way to learn spectroscopy or mass spectrometry is to solve problems. Okay. Now, any question before we go to the next topic? Yes.
How are both of them?
The 91?
Yeah.
How abundant is it?
No, how are both of them?
Okay, okay, good. The question that my wife is asking is, how come this here and this, how could they be 91, right? Okay, good. Here, this is where the attachment is. Here. Okay. Here, this is where the attachment is. Right here. You see that?
Yes.
Okay. So this here, if we add all the pieces together, the benzene fragment is 77. And the methylene fragment, where the attachment is 14. So that is 91. Okay, now when you come to this other species here, this here, the benzene fragment now, what would be the mass of the benzene? Keep in mind the attachment is here. What would be the mass? 76, exactly. So that would be 76. And of course, then you have the methyl is 15, right? Okay, that's a good question. So that is how you get N over Z 91 for each one of them. Okay. Now let us go back to. Okay, now we want to discuss infrared spectroscopy. Infrared spectroscopy is a lot more simpler than the mass spectrometry, so we will not be spending too much time on it. By the way, what time is it? 5? Oh, yeah?
7:15.
Or 7:15. I was hoping that we could finish all the 2 chapters today.
He always be saying it. Especially your damn
Okay. So now let us look at infrared spectroscopy. Now for the infrared spectroscopy, remember what we told you, the information we gather from here. What kind of information do we get? Functional group. That's what we get. The functional group. It gives us the functional group. Now, for the infrared spectroscopy, we are going to concern ourselves with light frequency in the infrared region right here. Okay? We are going to concern ourselves with the absorption of light by molecules in the infrared region of the spectrum, electromagnetic spectrum, which is this region right here. Okay? So therefore, infrared spectroscopy essentially is the absorption of infrared light by molecules. And we all know the energy of light, H over V, where the H is, of course, is the Planck's constant. I'm sure you all know that, right? And then the V is the frequency of light. Okay, very good. Now, of course, that could be translated to Planck's constant multiplied by speed of light divided by frequency. So we essentially measure the frequency of light, and if we consider the fact that the Planck constant, of course, it is a constant, the speed of light is also constant. So in essence, the measurement for the frequency here, or for the wavelength, this is the wavelength, is in centimeter in this region of the spectrum, in the infrared region of the spectrum. If we say that, so in essence, what we are simply saying here, we are going to be looking at what we call the reciprocal we are going to be looking at the wavelength of light, and so our measurement will be using reciprocal wavelength, which is of course unit of measurement is in centimeter. But to make life a lot easier for us, this reciprocal wavelength is generally referred to as wave number. And then we represent the wave number as reciprocal centimeter. Okay? So the region of the spectrum we are going to be looking at that is of concern to us is this region here, which is the region between 4,000 wave number and 400 wave number. That is the region of concern to us with regard to the infrared spectroscopy. Now, how does infrared spectroscopy work? At any given time, molecules will vibrate. There is vibrational motion in any given molecule at any given time. And the energy for that vibration is coming from the infrared light or infrared frequency. In other words, for the molecule to be able to vibrate, it must get the energy from somewhere, and that energy is coming from the infrared region of the spectrum. Okay, so all kind of vibration is taking place. Out of plane bending, stretching, symmetrical stretching, in-plane bending, all kind of motion is taking place. So what we measure is the absorption of light by molecules in the infrared spectrum. Now the good news is each functional group in any given molecule will absorb light in a particular part of that spectrum. Okay? For every given functional group will only absorb light in a given part of the infrared spectrum. Keep in mind we are concerned with infrared spectrum from 400 wave number to 4,000 wave number. Now, let us, for example, if you take a look at what we have here, of course, the absorption of light within that region is what we refer to as the infrared spectrum. So the absorption of infrared radiation by molecules is what we refer to as the infrared spectrum. Now in this particular instance, if you take a look at this molecule here, this molecule contains a carbon-carbon triple bond. Here, simply telling us this absorption here is due to the carbon-hydrogen stretch. So if I was given this sample, and that somebody tells me to determine what kind of functional group is present here, say, well, it is possible that you have a carbon-carbon triple bond. The same thing here. You have a carbon-carbon triple bond here. So each absorption tells you something about the functional group that is present in the molecule. I know you're going to say, well, how do we know all of this? You don't need to worry. We have a table of absorptions that we will give you whenever you have to take your quiz or your exam. You have this table. You could make up your own table and bring that table to your quiz and exam also.
So you tell me.
Okay, now, if you take a look at this slide here, these are the regions, these are the major regions of the infrared spectrum where you have useful infrared absorption. For example, if you see any absorption between this here, about 3000 to about 3006, what that tells you is that you have nitrogen bonded to hydrogen, or oxygen bonded to hydrogen, or carbon bonded to hydrogen. Of course, if you see any absorption in this region here, that tells you have a carbon-nitrogen triple bond or a carbon-carbon triple bond. Any absorption in this region here, what does that tell you? What does it tell you? Carbonyl, carbon-nitrogen double bond, or carbon-carbon double bond. Okay? Now, we could actually give you more details in terms of specific molecules, because this is just a broad overview of the regions of the spectrum that you have useful functional group absorption. Here, you have here. For carbon-carbon triple bond, absorption is in this region right here. The carbon-hydrogen bond to a triple bond, this is the absorption, 3,300. So you see a figure 3,300, what that tells you, the chances are you have a terminal carbon-carbon triple bond, in which case you have an hydrogen bonded to that carbon. Now, if you have the carbon-hydrogen bond of an alkane or and a carbon-hydrogen bond in which hydrogen is bonded to an sp3 carbon atom, that is where you expect the absorption. Folks, I will tell you right now, do not worry yourself about that absorption, because every organic molecule you have will have that. So it is a useless set of information. So, you know, which one?
Just that one that you think first?
Yeah, that's this here. The carbon hydrogen bond, in which hydrogen is bonded to a CH3 or, yes, to an sp3 carbon. Just about every organic molecule you have will have that. So it doesn't give you anything useful. Okay? Of course, carbon-carbon bond, that's useless also. Okay, you also have the carbon-hydrogen bond, about 3000 to 3001. That region is sort of, or sometimes overlaps with this region here. So that may not be too useful sometimes. Okay? Now, of course, you have the benzene. If you have benzene, you see absorption in this region, 1660 to about 2000. That would be useful sometimes. You have the carbon-carbon double bond in this region here. That region overlaps with the carbon-oxygen double bond. Okay, if you have an alcohol, the oxygen-hydrogen bond, you have that between 3400 and 3650. If you see that, you know you have an hydroxy group. What time is it? No, it's not time yet.
What do you mean?
It's not 7:30 yet. Did I tell you to stop? Okay. Okay, just let me finish this slide and then we go. Okay, so anyway, so what you have here, with respect to the infrared spectroscopy, you need to take a look at your book. All of the absorption frequency for different functional groups are given. However, for any quiz or exam that you take, we will be giving you a list of those absorption frequencies. But if you want to make yourself, you are also free to do that. Okay? Okay, at this point I will be stopping and then giving you back your exam. So when we come back on Thursday, we are going to start with nuclear magnetic resonance spectroscopy.